Okay, so hello, I'm Carol. Currently, I'm a postdoc at the Queen Mary University of London, but what I'm going to talk to you here about is the work that I did during my PhD, which was supervised by Raul Abramo, who's here. Before I start, I would like to thank the organizers of this event and the ICTP-SAIFR for giving this very nice prize for us. It's an honor to be here talking at this stage because it's ICTP here. This building is like my third home, so it's very nice to be finally giving a talk here. Okay, so I was going to start by talking, trying to motivate why to use large-scale structure, but I think that it needs no introduction given the crowd that we have here. And so I'm just going to use these slides as a sort of motivating and giving you a rough idea of the two topics that I'm going to discuss. Basically, with the large-scale structure, the interesting thing is that we have a huge volume of the universe that we can map if you compare it with the almost two-dimensional maps that you can have from the CMB. This is a lot of volume. And with more volume, we can sample more modes, and we can sample larger modes in a better way than if you are stuck with a small volume of the universe. So this gives us a nice way of doing statistics. And when we go to the larger scale, so if we can sample these larger modes in a better way, this means that we can go to larger scales where some very interesting effects start to appear in the distribution of large scale of dark matter tracers. One example, Raul briefly mentioned in his talk, is the non-Gaussian initial conditions of the universe, which leaves a very specific imprint on the bias of dark matter tracers. So if you break the Gaussian assumption using a specific kind of non-Gaussianity, what you have is that as you go to larger scales, as you're going to low wave modes, it means that you start to have some scale-dependent features on the bias of your dark matter tracers, for example, galaxies or dark matter halos. And this can be observed at the very large scales that you can measure. And this is something that is interesting to use the large-scale structure to do. And also at the larger scales, when we start to look at these effects, starting to analyze these very small K modes, what happens is that it is important to notice that the observations that we make in cosmology are done in our past light cones. So we are not stuck with a box that every point is in the same hypersurface of constant time, but what we actually observe is the structures as we see them on our past light cones. So this thing here will put imprints on these larger scales, and it is impossible, and it is very necessary to model these things if we want to properly understand theoretically what's happening with the dark matter distribution at the largest scales. And finally, with the large-scale structure, we can have a hint on nonlinear physics. We can go from a very smooth, initially almost Gaussian distribution, and as you turn on gravity, then what's going to happen is that these structures, which were very close to a Gaussian field, starts to collapse and form highly nonlinear structures. And this thing is not something that you can just discard. This is a very interesting thing because it will give us extra information about the distribution of dark matter on tons of scales. And also hints on the theory of gravity, for example. So I'm going to talk about a bit of those past light cone effects that we have on the distribution of galaxies and how we can use this nonlinear evolution of the gravitational field in order to improve photometric redshifts in a galaxy survey. So for the general considerations, what I'd like just to make a brief recap, also Raul mentioned this in his talk. Thank you, Raul, for doing it. So if we want to understand the large-scale distribution of dark matter, we can compute one of the cosmologist's preferable quantities, which is the density contrast, which is just the density that you have at some point, some x, y, z coordinate at some fixed time. You can subtract the spatial mean of that, and you can construct what is your density contrast. This gives you, you can use perturbation theory to understand how this thing is going to behave. And you can also think about when you're going to look at dark matter, what we are actually looking at, for example, is galaxies or dark matter tracers. And to do that, we compute the number counts. So we count how many galaxies we have in a pixel, for example, and we subtract the angle average of these. And then we can build a sort of density contrast, but now instead of a continuous density field, we use the number counts of galaxies. And the point is that different galaxies, for example, a blue galaxy or a red galaxy, as Raul mentioned, they are different tracers. They are going to trace differently the distribution of dark matter in the universe. And what this means is that when you compute, for example, your two-point statistics, so this is the Fourier transform of the two-point correlation function, the power spectrum here, what you're going to have is the presence of, for example, a linear bias, which can have different values for different tracers. And also, in the presence of those non-Gaussian initial conditions, what you could have is a k-dependence inside this object. So this is something that you need in order to properly understand how these different galaxies or dark matter halos will be tracing your dark matter field. So one example, and this is a slice of a light cone built from the relativistic n-bodied simulation devolution. So this simulation involves the Einstein field equations in the weak field limit, and gives you, it's an n-body code, and gives you, for example, as an output, the light cone containing, for example, dark matter halos. And this is a tracer that I'm going to use in the first part of my talk. So in this simulation, we have a light cone. So in the z direction here, this is the Cartesian coordinate, but you can associate this as you were looking at as redshift here. So different points here are at different redshifts inside the simulation. And this is just a slice through the y direction. And this is an example of how different halos, so each different color here is a different type of halo with a different mass, have very different linear biases. So this is what is meant, that B alpha is going to have different values. It's going to trace the dark matter field differently. And we're going to use these halos here just for the purpose of the next of this talk. So another interesting thing to do is that, okay, when you look at here, this is your Cartesian coordinates, for example, at some fixed time. But what we actually observe is some angles in the sky, so theta phi, and some redshift that you measure from some galaxy survey. And this is a credit from Camille's Bonvin talk. But what happens is that if you have a perfect 3D Robertson-Walker universe, which is unperturbed, then the photons emitted by a source would follow a straight path until reaching us here, the observers at our detectors. And then it would be a very straightforward thing to compute what is the x, y, and z coordinate of the source, because you know exactly that this photon followed this path here. However, in the universe, we have tons of stuff between the source and the observer. We have matter in the middle that is lensing the source. So, for example, what happens is that the source here, which emitted a photon, the photon was distorted throughout its path until hitting us here. And then when we look at this object with the angle and the redshift that we measured, we can actually place the source in a different location than what it really is in reality. So this gives rise to distortions in how we model, theoretically, the number counts that we measure. One particular example of this is Redshift-space distortions. So this is a distortion in energy of the photons. This that I'm showcasing here is just the Kaiser effect. So if you have the observer here looking along this line of sight, and you have three galaxies, okay? So the fact that this galaxy has an inward velocity here following towards this other galaxy, and the galaxy 2 have a velocity in the opposite direction. When you project this thing along your line of sight, what you're going to see is a squashing in your two-point correlation function. It has been shown in many talks here, in particular, Raul also showed this. If you start entering the nonlinear regime, you start to see the fingers of God here. This is just showing the linear case. So basically, the fact that you have a velocity which you're projecting along the line of sight will add on top of the redshift that you would have from a pure 3D Robertson-Walker space-time. So this is a shift in coordinates, and this must be accounted for. one thing that I would like to call your attention is that this thing is symmetric along the line of sight. So if you look this way, it's going to be exactly the same picture. It is completely symmetric when you look at the parallel direction. So this brings me to the distortions that I studied in my PhD, which is these relativistic features in the clustering of dark matter halos. And I like to show this picture because I think this is very intuitive to summarize the kind of effect that I was looking for in this work, which is basically now if you think about this as a gravitational potential, and you have a bright galaxy here at the bottom of the potential, in order for us here at the observer to observe these galaxies, they have to emit photons, and these photons have to climb out of the gravitational potential. So these two galaxies here that I'm calling faint, so these are two different types of galaxies, will emit photons that will have to climb a certain amount of gravitational potential in order to escape and reach us here. So these two galaxies will suffer a particular redshift here, and they will be, instead of located here, we will think that they are actually at these positions. While the bright galaxy in the very bottom of the potential, the photon emitted by it will have to climb a much higher steep in order to escape and reach us. So this galaxy suffers a larger gravitational redshift than the other two galaxies. And if you put this against the line of sight, you're going to see that a situation which was originally symmetric, so these galaxies were exactly at the same distance from the bright galaxy, now they will exhibit an asymmetry along the line of sight. So something that was initially symmetric now becomes asymmetric. And this thing will introduce a dipole. So this is just to show the theoretical expression for the number counts of galaxies at any dark matter tracer as you observe at a certain angle and redshift. And particular, this one here is the effect that I just give you as an example. This would be the effect of the gravitational potential, redshifting the photons. Then you have here the standard Kaiser effect, which is just the Redshift-space distortions, traditional effect. And here you have effect of magnification bias, which is associated with lensing. And the interesting thing is that if you look at this expression, these three terms here, they cancel if you are assuming the equivalence principle, meaning that this kind of full expression, the full thing that we have in general relativity can actually give us a clue on, for example, if the equivalence principle is holding or not. And this has been studied by Camille Bonvin and her group in Geneva, how you can use this to test this assumption for dark matter particles. So I'm going to, in this work, we focused only on the projection along the line of sight. And why so this is the main quantity that we are working with, given its expression. We are neglecting the integrated terms and the things that depend, that does not depend on the projection of the velocity along the line of sight. And if you do that, if you consider only these terms, and you Fourier transform your overdensity of your number counts, you can compute the Fourier two-point correlation function on the power spectrum when you cross-correlate different types of galaxies. So that I showed two faint galaxies and a bright galaxy, which could be alpha and beta, so two different objects that trace differently the dark matter distribution. And when you compute it, you see that this expression appears, and this thing here is proportional to the projection along the line of sight. So you can use the Legendre decomposition to extract its moments. So in this particular work, we tried to see if we could find this dipole in the power spectrum of Redshift-space dark matter halos from the devolution simulation. And one interesting thing to look here is that this depends on this parameter A alpha. A alpha is carrying information from your tracer, such as magnification bias, evolution bias, and quantities that are actually important when you try to model the large-scale structure, because these things here encode the evolution of your tracers throughout the redshift. So it is important if you're trying to do analysis in the past light cone. B alpha here is just the linear bias of the tracers, and F is the growth rate of structure. As a result, we unfortunately could not claim a detection. We can, so solid here is the predictions that we have for that dipole. And the points here is the things that I managed to extract from the simulations by estimating this dipole directly from those dark matter halos. The important thing to keep in mind here is that we had a light cone simulation. We managed to take the halos, to construct the halo catalog, and to develop the pipeline to try and measure this effect. The problem was that the simulation was not big enough, and we could not claim the detection. But now we have a pipeline, and we have a larger understanding on how to do that, maybe with larger simulations, and maybe even apply that thing to data. So I'm going to skip now to a very different subject in the remaining of my talk, which is something that I did with these people here. This was actually an idea of Davi Alonso, and we developed this in the last year of my PhD, which is using the bispectrum now, not the power spectrum, but the bispectrum between galaxies and intensity mapping, in order to improve the measurements of photometric redshifts. So I'm going to explain this a bit better. So when it comes to analyzing the large-scale distribution of dark matter with discrete tracers such as galaxies, dark matter halos, or quasars, for example, we are trying to sample very large volumes of the universe with these discrete tracers. And one of the things is that we have to overcome shot noise. So if we want to have enough objects in order to detect these effects that will appear on the very large scales of the universe, we need very dense samples. And as Antonino showed in his talk about Euclid, if you have the photometric survey in Euclid, you can get of order 10 billions of objects, while if you go to a spectroscopic survey, you have of order of 10 or 30 million objects. So it's clear that if you do photometry, which is a faster way to get a rough estimate of your redshifts, you can get an order of magnitude more objects in order to do this kind of analysis. So this is very nice when it comes to overcoming the shot noise that you have. And basically, broadband photometry is going to take these strong spectral features and guessing what is the redshift of this objects instead of putting this thing through a spectrograph and getting a very precise measurement of the redshift. So when you do that, one thing that you have is that you have large uncertainties on your redshift. And here I'm showing the redshift distribution of sources. In black is what you would have from a spectroscopic survey, where you know that a galaxy at redshift of 1 is exactly a redshift of 1. However, if you're doing this with photometric redshifts, you have an uncertainty associated with this galaxy, meaning that a galaxy which is a redshift of 1 can actually have a certain, it can be plus or minus something which is non-negligible. So you have a large error in your redshifts, which I'm parameterizing by this parameter sigma z. So the larger this value, the more uncertain your redshift is. And if you miss this radial information, so if you are blurring the galaxies along the radial direction, the presence of these photometric errors is acting as a sort of Redshift-space distortion because you don't know exactly where you're placing the galaxies, so you're blurring things along the radial direction. And when we don't have this kind of information, we usually project the galaxy field, the three-dimensional field, with this selection function along the radial direction, and when we work in the tomographic beams that surveys like DES do. So this is, there is a problem here that, so we are talking about these photometric redshifts that will have this dumping along the radial direction. And this dumping, I'm modeling here as an exponential, as a Gaussian dumping. This will remove the very large K parallels. So you're losing information from your small scales when you have these photometric uncertainties. And this is because you don't know how to place the galaxies along your radial direction. So this is the accessible modes in Fourier space. It's in the pink region by the broadband kind of photometric surveys. And this, if we want to actually recover this distribution, if you want to know what will be the redshift distribution of the sources, we can try calibrating this sample that we have, this photometric sample, with some sample that we know the redshift. So for example, a spectroscopic survey. However, when it comes to cross-correlating galaxies from a photometric survey with spectroscopic surveys, we have a geographic non-overlap. So they sample different regions of the sky. So we can use actually intensity mapping to do that, because there is an overlap between photometric surveys and 21 centimeter intensity mapping surveys. But the problem with intensity mapping, I'm not going to go into the details because this is very technical, but you can ask me later, is that the foregrounds that you have to remove from the intensity mapping in order to do cosmology with is going to dump all the very large scale modes, because this is where you have the degeneracy between your cosmological signal and your foregrounds. So you don't know how to model these, and these scales are usually dumped, or you simply remove them from your problem. So if you think about cross-correlating galaxies with intensity mapping, you see that the overlapping region here that you would have in Fourier space to do this cross-correlation is very limited. So all this red region here is not accessible by the intensity mapping. And the pink region, so the only remaining region is this where the pink overlaps the green. So it's a very constrained space that you have to do these cross correlations. So in order to proceed, we decided to use the bispectrum. I'm just going to briefly remind you what it is. So as the two-point correlation function, you measured how 2 points correlate in space. With the bispectrum, we're going to look at triplets of galaxies instead of 2 galaxies only. And here, for example, we're going to look at the excess probability of finding these kind of triangles. We could also look at these collinear shapes here. So basically, when you look at the bispectrum, what you're seeing is that you have a high probability of finding things that are in these two when they are collinear, or when they are, on the other direction. So when you open completely this triangle or you close it completely. So this you have the higher probability, and meaning that you are looking at filaments and these structures. So this is an example of how the information of the bispectrum. And the bispectrum will appear due to the very nonlinear structures that we form in the universe due to gravitational evolution. So if you only have a Gaussian initial field and you have no nonlinear physics, then you wouldn't have a significant signal for the bispectrum. So it is basically telling us how different modes will couple in the large-scale structure. So it's just to show how we can model the bispectrum. The power spectrum, the cross-power spectrum between two different tracers will have some certain kernel here that carries the bias of these different tracers, and you have the shot noise that will appear, which would be 1 over the number density. For the bispectrum, we have the dependence on the power spectrum that appear here, these combinations, and you also have the intrinsic power bispectrum of, if you have some non-Gaussian initial conditions, for example. And these will carry dependencies on the linear bias and higher order biases that you have in your large-scale structure. So what we try to do is basically to reconstruct the modes that we lost due to foregrounds in the 21 centimeter intensity mapping. So as I was mentioning, for the for the intensity mapping survey, you are losing the very large scales. So you are only retaining the very large K modes. So you only access very large K Fourier modes here. While for the galaxies, the other thing is happening. So for the galaxies in a photometric survey, you are completely losing the very small scales, meaning that you are only retaining the very small K Fourier modes. And when you look at the bispectrum, you have actually a coupling between these different scales. So if you do the cross-correlation between the galaxies, which you have access to the very long wavelength modes, you can actually try to recover this thing in the 21 centimeter survey, which you only have access to the very small scale fluctuations, because this thing is modulated by the long wavelength fluctuations, which is captured by the bispectrum. So this was the idea of cross-correlating galaxies with the 21 centimeter at the bispectrum level. And when we do that, we find that by using the bispectrum, so the dark blue region, I'm showing how you, the errors, the forecasted errors on the center, so how well you're placing your, the redshift of your galaxy, how right you're guessing which is the redshift of a photometric galaxy, and on the width of that distribution. So we can actually recover those, that selection function that I showed. And, sorry. And here what I'm showing is the constraints obtained with the bispectrum, or just by doing the cross-correlation between galaxies and intensity mapping at the power spectrum level. So as you can see, as we go along in redshift, for the bispectrum, you are very well, it is a very well-behaved curve, and it is completely under the Y10 requirements that you have for these two parameters of your redshift distribution for the LSST survey. While for the power spectrum, depending on the errors that you have on the photometric redshift, your constraints are completely lost if you try to do this thing with the power spectrum only. So the take-home message of this work is that using the bispectrum, if you're trying to combine galaxies and intensity mapping to recover your photometric parameters, is highly recommended because with the bispectrum you can recover those modes that are in principle lost to foregrounds. So this is just a summary of the things that I did in my PhD. From the relativistic effects kind of analysis, we saw that a dipole signal appear when you start to include relativistic corrections in your power spectrum. We developed the pipeline-edge model, estimate and interpret the dipolar modulation that we have by these relativistic effects in the three-dimensional clustering of halos obtained from the fully non-relativistic simulation. We neglected the integrated effects in this analysis, and no dipole detection could be claimed with our simulations. From the clustering redshifts point of view, how we can use gravity to help us constraining parameters and improving the photometric redshifts, we employed the multiple tracers technique to combine the photo-Z galaxies with intensity mapping. We used the bispectrum because with the bispectrum we can have this mode coupling, and we can recover the nonlinear, we can recover the large radial scales that we 21 centimeter intensity mapping apparently lost to foregrounds. And the bispectrum is capable of calibrating your redshift distribution in situations where the two-point function is not. So I'll leave it with the conclusions. Thank you for your attention.
Go upstairs. So you compare with G-evolution simulations, right? Because you need relativistic effects and everything. Is it possible to paint relativistic effect on top of n-body simulation, Newtonian simulations?
Yes, it is. So if you have access, for example, let me go back to the expression. So the whole idea is to mimic these effects. So if you have access to your, if you pick any body simulation, a Newtonian one, if you have the velocity field, you can put your dark matter particles or halos in Redshift-space just by doing this transformation here, right? The standard transformation in your redshift. If you have access on top of that to the gravitational potential, you can include the effect of the gravitational potential in your any-body simulations, and then you would be mimicking this particular piece of the distortions. So in principle, if you have access to these quantities, you can do whatever you like, even if it is a Newtonian one. The only thing is that you would be putting by hand and you would be extracting the same effect, but yes, in principle you can do that.
Any other question?
Actually, I have an announcement if there are no further questions. Okay, conference announcement. Tomorrow, seminar by Elena has been cancelled because she's not well. So Archieman, you talk at 11, okay? Yeah. And this is specifically very good because tonight at 7 we have the dinner, and who knows after the dinner. At 7 at Bovinus, you have the map.
Okay, let's thank all the speakers again.